So hey guys, welcome back to my channel. In today's video we are going to solve the problem trapping rainwater. Okay, so let's start. So the trapping rainwater is a medium level problem in DSA. Okay, given n non-negative integers representing an elevation map where the width of each bar is 1. So and compute how much water it can trap after raining. Okay, so I have created bars. Okay, so these are the bars and the each of the bars width, so its width is 1. Okay, for example, if it is raining, okay, and suppose it is raining here. After raining, in bars, how much water it gets filled, or how much water will the bars will trap. Okay, so the water will trap in this or in this also. Okay, so after raining we have to find how much volume of water will be trapped in between the bars. Okay, so we have given the height of each bar. Okay, so the height of each bar will be, so this bar is 4, here 2 0 6 3 2 and 5. So the bar's height is given as the form of array. Okay, we have to take the height as array. Okay, so we have to find how much volume water will trap between the bars. Okay, so suppose there is a bar, this is the single bar, and uh, suppose there is some water, it's trapped on the bar. So the here's are some bars and here is some bar. Okay, then only the water will trap. No, there is no bar both the sides, then the water will spill out. Okay, we know the bar width is 1, and let's take the bar's length as x. Okay, and a total till the water is stored we take as w. So how can we get our volume of water? So simply we have to remove total height minus the bar's height. Okay, so we can get this much of our trapped water. Okay, as well as we have to multiply it width. Okay, so I have ignored width because width is 1. Okay, all bars width is 1, so that's why I have ignored. But it's suppose the width is greater than 1, then we have to include the width also. But in this problem we have taken the width of the bars as 1, so we not need of it. Okay, so we can simply ignore it. From this, can I say water level minus height of bar and multiply by its width is equal to trapped water? Can I say this? Yes, we very logically, and we have derived this formula. Okay, I have drawn the bars as above. Okay, so after raining, the water will trap in this area only. So somewhere else and here. Okay, then if the water is filled above this bar, okay, the water will spill outside. Okay, spill from here. Suppose the raining is more, and if he fill the water till this, it will spill from this. Okay, so it will not, this area will not trap the water. Okay, the water will only trap between two bars. Okay, so from this bar the water will not trap. So from here the water will trap because we have boundaries. We have two bars, and in two bars only the water will trap. If there is a single bar, then the water will not be trapped. Okay, so let's analyze how much water will it trap. Okay, we can see, so in bar first the length is 4, and here we do not have any left boundary, so the water will not be trapped and this will be 0. Okay, let's come to second bar, and this above this bar, how much water will trap? So it will trap till this. Okay, so water will trap till 2 minus the bar's width. Okay, this will be 2. Okay, so water will trap with this only. Then here the bar's length, here there is a no bar, so the water will trap till left boundary, that is 4. Then here, so we do not have left boundary as well as not boundary, so it will trap 0. Okay, you have to simply draw this formula here. Okay, so from this bar total width is 5. Okay, and the bar's width is 3, so we have to minus it with and multiply with the width is 1. Okay, then how much water will trap? Here only 2 volume of water will be trapped in upon this bar, so 2. Next, on this bar 2's bar, so the water will trap 3. Okay, 3 volume of water will trap, and from this bar, this fifth bar, the water will be not be trapped because we do not have any right boundary here, so 0. I have to add this, and so 11. So we need this answer. Okay, so let's take some cases. Okay, so suppose first case will be, suppose there is a single bar, and will and suppose the water has been fall here. Okay, so it will not trap any water, the water will spill from here and here. The single bar will cannot be trapped the water. Okay, next case will be, let's take 2 bars. Okay, in this any water will trap? Obviously no, because if water will fall on this bar, the water will spill out from here. Okay, from here also, so water will not be trapped in this bar also. So water will fall on this bar, so the water will spill out of this bar also. So this also, okay. So in this bar also the water will not be trapped, okay. Water will fall on these bars, okay. Bar on also the water will not be trapped, okay. The water will spill outside, okay. So in three of the cases the water will be not be trapped. So to trap the water we need uh, greater than 2 bars, okay. So then only the water will trapped. Let's take an example. So suppose the bars are in ascending, okay, or descending. So I have drawn descending bars. If the water will trap on this, no, because if the water will fall on these bars, the water will spill outside here and the water will not be trapped also, okay. On this bar the water will fall, the water will spill outside because the water will not be trapped on this, okay. So suppose its height is 6 6 and 2, so then only the water will trapped on this, okay. One more example. So if the water will fall on this bar, then the water will trap till the lowest bar, okay. The water will trapped until it reaches to this maximum of lowest bar only, okay. Taken the bars, for this bar the width is 10 6 2 and 8, okay. Then if the rain will falls on these bars, then the water will trap until the lowest bar, okay, of this lowest bar only. Here the water will not be trapped because here we do not have any boundary, okay. Maximum right boundary and this is the maximum left boundary. So here we can see that the maximum right boundary and maximum left boundary. So what the maximum right boundary shows that it is the capacity of water to store in right side, as well as we can see that in left boundary the capacity of water it will store in left side. So it's showing that, okay. And here we have to get the minimum of it, okay. So we have to calculate maximum of left and we have to calculate maximum of right, and then we have to take its minimum. So we will get this trapped water, okay. So the conclusion is, so water level will be, okay, so we have to calculate max left and max right, and we have to take minimum of it. So suppose we are on this bar and we have to calculate its maximum of left, okay. So maximum of left is 6, okay, and the maximum of right is 4, okay. So the water will trap in this between, so we have to calculate its minimum, okay. And in, so its corner cases will be minimum number of bars should greater than 2, okay. And in ascending bars or in descending bars the water will not be trapped, okay. So we know that we have seen the cases. Okay, seen the formula. So trapped water will be water level minus height of bar. Okay, multiply by width. So width is always 1, so we can ignore the width. Okay, so we know the height of bars, so to just know the water level, so the water level will be maximum of left boundary, maximum of right boundary, and we have to take its minimum. So this will be the water level. Okay, I have drawn this diagram, and now let's take this bar. Okay, so what is the maximum right boundary of the for this bar? This is this 6. Okay, and what will be the maximum left boundary for this bar? Will be before. We have to take its minimum. That will be the water level only. So its water level will be 4. Okay, and here in this formula we can see the height of the bar. The height of the bar is also 4, and into width, the width is 1. Okay, so we can ignore it, but in the formula we have written that. And the trapped water on this bar will be 0. Okay, so like this way we can calculate each of the bars trapped water. Okay, so let's take another example. So this bar, so left maximum is 6. Okay, and right maximum is 5. So we have to take its minimum. So minimum is 5. Okay, and minus the bar's height. So bar size is 2 into 1. Okay, so this bar will trap the water 3. Okay, so like this we can calculate each of the bars water will trapped, and then so we have to add the total trapped water and we can get our solution. We have to create this two auxiliary arrays for, okay, one for maximum left boundary and one for maximum right boundary. Okay, so let's take this. So for this bar, what will be the maximum left boundary? The 4 only. For this bar, what will be the maximum left boundary? Obviously 4. For this 4. For this bar, what will be the maximum left boundary? 6. Obviously this is the highest bar. For maximum boundary 6 only. So for this bar, what will be the maximum left boundary? 6 only, and for this bar also 6. Right max boundary where we have to traverse from right side. Okay, so for this bar, what will be its maximum right boundary? Obviously 5 only. For this bar, what will be its maximum right boundary? Obviously 5. For this bar, what will be its maximum right boundary? 5. 6 only. For this bar, what will be its maximum right boundary? 6. For this bar, what will be its maximum right boundary? 6. And for this bar, what will be its maximum right boundary? 6. We have calculate for each and every bar its maximum left boundary and maximum right boundary, and we have to take its minimum. Okay, for this 4 and 6, what will be its minimum? So its minimum will be 4, so we have to take 4. According to this we have to calculate. So let's take another example. So for this bar, okay, so this bar is on 0 1 2, 0 1 2. Okay, so its left boundary is 4 and right max boundary is 6. So which is the minimum? So minimum is 4, we have to take, and we have to minus its bars height. So bars height is 0. So how much water it will trap? It will trap only 4. Okay, so like this we have to find trapped water. Okay, so thank you for watching this video.